We'll work two quick practice problems here to get us warmed up for to apply molecular orbital theory in organic chemistry too. All right, let's go. Take a minute, pause, and answer this question just as best as you can. This warm-up will work the best if you actually try yourself and then work through it with me. All right, goodbye. See you in a few minutes. We're going to draw the Lewis structure for acetonitrile. Now, this might be intuitive to you at this point. Hopefully it is after a semester of organic chemistry, and it may not be intuitive. One thing to keep in mind if you are a bit rusty is that these condensed structural formulas imply connectivity. That CH3 means that there's a carbon atom with 3 hydrogen atoms bonded to it, aka a methyl group. Bonded to that is a carbon bonded to a nitrogen. We know that carbon typically makes 4 bonds, so it's most likely bonding 3 times to that nitrogen in a triple bonding interaction. And then nitrogen usually makes 3 bonds with a lone pair. So we think that this is probably the correct structure, but you can also just follow the full guidelines for drawing Lewis structures if you need to, and you can review that from Organic Chemistry 1. So here's our full Lewis structure. Our next task is to describe the bonding between the carbon and nitrogen atoms. How would you describe that bonding interaction? Yes, this is a triple bond. There are 6 shared electrons total, 2 per bond. We might describe this bonding interaction as 1 sigma and 2 pi bonds. And this describes the symmetry of the orbitals making the bonds or holding the bonding electrons. In order to fully describe the bonding, we might consider the hybridization of the 2 atoms making the bonds. We'll call this C1. C1 is an sp hybrid with linear geometry. If it's an sp hybrid, it contains 2 sp orbitals at a 180-degree angle from one another. That's where this linear geometry, this 180-degree bond angle, where that comes from the sp hybridization of the carbon. Of course, as we talked about in Organic Chemistry 1, hybridization is not real. That doesn't actually happen, but we still pretend it does because it's a very good predictive tool. And then sp hybrids have 2 p orbitals left over with which to make pi bonds. These are perpendicular to one another, and the p orbitals can make pi bonds. Nitrogen is also sp hybridized. That's how we would consider it as well. So it has the same types of orbitals and can do the same things with it. Okay, let's draw out the bonding interactions. So carbon will use one of those sp orbitals to bond with nitrogen, which will also use an sp hybrid orbital. These orbitals come together in a head-to-head fashion. There is cylindrical symmetry of electron density around the bond axis. That makes this a sigma bond. The cylindrical electron density about the bond axis makes this a sigma bond. Right, so carbon used one of those sp orbitals to make this sigma bond with nitrogen. It's using the other sp orbital to make this sigma bond with the other carbon. So it's using that sp orbital, and this carbon's using an sp3 orbital, and they're making another sigma bond here. But we're not worried about that right now. We're just worried about the carbon and nitrogen atoms. Okay, now that we've described this sigma bond, let's describe the 2 pi bonds between these 2 atoms. So each of them has a p orbital left over after hybridization. So that's the p orbital from carbon. Here's the p orbital from nitrogen. And these p orbitals can come together in a side-to-side fashion. There'll be overlap above the bond axis and overlap below the bond axis. So I can show the overlap like this. You might also be used to seeing a pi orbital or pi bond shown like that. Both ways are okay. You can use either drawing to indicate that there is a pi bonding interaction. Now, this is called a pi interaction because there is electron density above the bond axis and below the bond axis, but there is no electron density on the bond axis, right? There is a node on the bond axis, otherwise known as the internuclear axis, for the pi orbital. So that is how a pi orbital, a pi bond, is different than a sigma bond. The pi bonding has electron density above and below, but not on the bond axis, so not directly in between the two atoms. Whereas the sigma bonding interaction has electron density about the bond axis, including on it. So typically sigma bonding interactions are stronger than pi bonding interactions for this reason. So now we've shown one of the pi bonding interactions, we need to show the other. We've used up this p orbital from carbon. There's one p orbital left, and it is perpendicular to the one that I've shown in green. By perpendicular, I mean that the orbital is aligned with an axis at a 90-degree angle from the axis along which the other p orbital is aligned. So technically, these p orbitals are coming in and out of the plane of the page. It's just easier to draw them this way. There is overlap here and overlap on the other side of the bond axis. So this is another pi interaction between these two p orbitals. Excellent. We've described the triple bond between carbon and nitrogen. There is one sigma bond and two perpendicular pi bonds. The sigma bond is made from hybrid orbitals, from the sp orbitals from both atoms, overlapping along the bond axis. The pi bonds are made from the leftover p orbitals, the ones that were not used to make the hybrid orbitals, and those two sets of p orbitals are perpendicular to one another. There is a 90-degree angle between the axes along which they are aligned. And so there are two perpendicular pi bonding interactions that result as well. Just a quick review before we move on. Hybrid orbitals, they are used to make sigma bonds and hold lone pairs. So for example, nitrogen is using one of its sp orbitals to make the sigma bond. The other sp orbital is holding the lone pair. And then these leftover p orbitals, the ones not used to form the hybrid orbitals, these are going to make pi bonds or be empty. Okay, so keep that in mind as we move forward. Now that we've reviewed valence bond theory, let's review some molecular orbital theory. Pause and start by drawing a complete molecular orbital diagram for acetonitrile. Then identify the frontier molecular orbitals for this molecule. Just do the best that you can here. By molecular orbital diagram, I mean an energy diagram. I would like for you to include the types of orbitals and their relative energies and how many electrons are in each orbital. So type of orbital, so its name like sigma Cn, relative energies, and the electrons. So which orbitals are they in? So to start, we need a Lewis structure. We've drawn that in the previous problem. Then we need to identify the types of bonds, describe the bonding. We got started on that in the previous problem as well. Now we have to consider the entire molecule, and that makes our task a little bit more tricky, but we can do it. There are 3 sigma CH bonds. There is 1 sigma C bond, 1 sigma Cn, and 2 pi Cn. And finally, let us not forget the lone pair. So we can call this non-bonding on nitrogen. You could say it's an sp orbital if you want, but really, even though we could call this a lone pair and we pretend those electrons are on nitrogen, they're really in a molecular orbital spread out on the entire molecule. But let's not make our brains hurt too much. We'll call this non-bonding nitrogen. That's how we'll describe it, the lone pair. But yes, technically it is in a molecular orbital. Great. Now we've described the lone pair and the bonding orbitals. But we know that for every bonding orbital, there is an anti-bonding orbital. So let's also list the anti-bonding orbitals. We can't forget those. There are 3 sigma CH. There are also 3 sigma star CH. So 3 bonding orbitals and 3 corresponding anti-bonding orbitals. If there's 1 sigma CC, there's 1 sigma star CC orbital, a corresponding anti-bonding orbital. If there's one sigma Cn, there is also one sigma star Cn, the corresponding antibonding orbital. If there are two pi Cn orbitals, there are two pi star orbitals. And finally, this non-bonding, there is no antibonding associated with the non-bonding, it's just a non-bonding orbital. Okay, now you have to put the orbitals on the chart in terms of relative energies. Generally speaking, the lowest energy type of orbital will be sigma, and then a pi, and then non-bonding, and then the antibonding orbitals, pi star and sigma star. And for more details, you can review the full lesson from Organic Chemistry 1. We have identified several types of bonding orbitals in acetonitrile. We've identified sigma CH, sigma CC, sigma CN, and pi CN. These all represent bonding orbitals, and they will be the lowest in the lowest energy group of molecular orbitals. Now, we know that sigma is lower energy than pi, as we described during the previous problem. And within the sigma group, orbitals from more electronegative atoms will be lower energy. So the lowest energy molecular orbital for this molecule will be sigma Cn. Okay, sigma Cn right here. Check. That's the lowest energy orbital because it is derived from carbon and nitrogen, and those are the most electronegative atoms of the ones that we're considering in this problem. Next lowest is sigma Cc. And then next lowest will be the sigma CH orbitals. Okay, so what all three of these orbitals have in common is carbon, and nitrogen is more electronegative than carbon, which is slightly more electronegative than hydrogen. So the sigma Cn is the lowest energy, then sigma Cc, and then sigma Ch. Orbitals of the same type, so these are all sigma orbitals that are derived from more electronegative atoms, have lower energy. All right, next, pi bonding orbitals. There are two pi Cn orbitals, and those will have the same energy. They are degenerate. They have the same energy. Now, non-bonding, there is that non-bonding pair of electrons on nitrogen. And now it's time for the antibonding orbitals. Pi star orbitals are lower energy than sigma star, so those pi star Cn orbitals come next. Just like the pi orbitals, the two pi stars have the same energy. They are degenerate. And now finally, our last group of orbitals is the sigma star orbitals. And we will use the same relative order of energy as we did for the sigma orbitals. So those derived from more electronegative atoms are lower energy. So sigma star Cn is the lowest energy sigma star, then sigma star Cc, and finally the sigma star Ch orbitals. Now we will put electrons in orbitals. We can count the total number of electrons in the Lewis structure. There are 2, 4, 6, 8, 10, 12, 14, 16 electrons. And we should put those 16 electrons where electrons go, which is the lowest energy orbital possible. So 2, 4, 6, 8, 10, 12, 14, 16. And then you just want to check to make sure that things make sense. So what does that mean, things make sense? Well, the bonding orbitals should be full. The antibonding orbitals should be empty or unoccupied. Now, not always, but usually. And then you want to make sure your lone pairs are there, right? So if you have a filled non-bonding orbital, like in this case, then those electrons should be there. Excellent. So our diagram looks good. You can also, if you're checking the diagram, just make sure that for every bonding orbital, there's a corresponding antibonding orbital. But we did that earlier. But just if you're double checking, you can check that. Our last task in this problem was to identify the frontier molecular orbitals for this molecule, and specifically the HOMO and the LUMO. In case you've forgotten or in case you didn't learn this in Organic Chemistry 1, it's okay, don't panic. Let's just quickly define some of these terms. So first, frontier molecular orbitals. These are often abbreviated as FMOs, and you can think about them as being on the frontiers, on the edges. The edges of what, you ask? Well, I will show you in a minute. HOMO, this is the highest energy occupied or filled molecular orbital. Okay, so highest energy filled or occupied molecular orbital. And then the LUMO is the lowest energy unoccupied or empty molecular orbital. Now that we recall these definitions, let's apply to this problem. Okay, so highest energy filled or occupied molecular orbital, that's on the edge of the filled orbitals. And then for this molecule, that would be the non-bonding pair of electrons. That is the highest energy of these orbitals that are occupied with electrons, right? We choose amongst these orbitals, and the non-bonding pair of electrons is the highest energy filled orbital. Now, pi star, Cn, these are the lowest energy amongst all of these empty orbitals. So these two pi star Cn orbitals, these are represent the LUMO for this molecule. Right, easy peasy, right? So you want to have this skill, just be able to identify the HOMO and LUMO for a given molecule, given its molecular orbital diagram. If you need to go in depth on any of these topics, so this problem or the valence bond theory problem, please contact me and I can direct you to the appropriate reference. It's no big deal. We have some time now to review topics that we need to review. So be sure that you let me know if you need some extra help. All right, let's get going deeper now into how molecular orbital theory is applied and important for organic chemistry too. We're done warming up.